Hi everyone, I hope you all are live and you should be able to hear and see me. You can just say yes.
You all are live and you should be.
Is it audible to everyone? Audible as well as visible? Okay, great. So this was today's question, seat reservation manager. Uh, so to start the discussion, how many of you were able to solve this question? It is a very conventional question, one of those questions which is very much asked in interviews, and there are so many variations of it. There can be so many variations of it. So I'm just curious to know that how many of you were able to code it on your own. Also, in the meantime, okay, you didn't get chance to attempt it. Okay, in the meantime, we are just going to read the question. Okay, so let's read it. It says that we have to design a system that manages the reservation state of n seats that are numbered from 1 to n. So the first thing it says is that we have got some seat numbers. Let's say these are the seats of a train, which are 1, 2, 3, 4, 5, so on till n. Okay, now what we have to do is we have to implement a seat manager. Initially all these seats are not reserved, so all these seats are empty, anyone can reserve them. Now if you look at it, there is a class called a seat manager which has a constructor. This constructor takes in the number n, which tells you how many seats are there, and also it says that initially all the seats are available. Now there are two important methods, reserve and unreserve. Reserve, it does not take any input, it simply returns an output. So what it does is it fetches the smallest numbered unreserved seat, reserves it and returns it number. For example, let's say initially all these seats are vacant and reserve method is called. What will happen? What will happen? If you read these lines, we will fetch the smallest numbered unreserved seat. So what is the smallest numbered unreserved seat? It is 1. So we will fetch this 1 and we will return this 1. That's it. Okay. So let's say somebody calls reserve again, then what will happen? The smallest numbered seat, which is still not reserved, is 2. So 2 will be fetched and returned. Let's say somebody calls reserve again. In that case, as we can speculate, 3 will be returned. Somebody calls again, 4 will be returned. So this is how it goes on. Apart from that, there is another method called as unreserve. So unreserve is the opposite of reserve. It takes an input but it gives no output. So what it does is it takes a seat number and then unreserves it. So think of it in this manner, that there was a person who had booked seat number 2 in the train, and now if he cancels his ticket, he or she cancels the ticket, then seat number 2 will be unreserved. Because it will be unreserved, so it needs to go back to that. Now when it has been unreserved, when it has been freed, at this point of time, if somebody calls a reserve again, can you tell me what should be returned? These seats are currently available and somebody calls a reserve again. If you read the documentation of reserve, the value 2 should be returned. Good. Yeah. So this is pretty much it. Now what we have to do is we have to implement these methods and constructors. That's it. Okay. So so tell me, what is the simplest idea which comes to your mind to start with? Let's start with a very naive solution. Okay, the first thing you can think of is min heap. So somebody is immediately talking about a min heap, which is very good, that you can think about an optimized solution right away. So anyone here who does not know about heap? Never dealt with heaps or priority queues? Anyone like that? What I can say is that to start with, the simplest approach which comes to our head is let's have an array, and let's give this array a name called as seats. To start with, it can contain all the seats which are unreserved, and it will contain them in an ascending order. So let's say we have 1, 2, 3, 4, 5, so on and on and on, n minus 1, and finally n. Okay. Now what we can do is that whenever a reserve method has been called, in that case what I'm going to do is I'm going to just return the first such seat which is not occupied yet. So maybe what I can do is I can return this 1, and after returning this 1, maybe I can mark this location. So let's imagine these are indices of an array. Index 0, 1, 2, 3. 0 I am neglecting, but let's say these are indices of an array. Now whenever a particular seat has been allotted, then at that index you can probably do a true. You can say that it has been allotted, right? Now let's say somebody calls a reserve again, then you can do a true here. Somebody calls a reserve again, you can. So marking them true is like you are freezing those seats, you are reserving those seats, right? So this is how you can keep going on and on. But there is a trick here. The trick is that whenever somebody calls unreserved for a particular seat number, let's say somebody calls unreserved for seat number 2, then you have to mark it back to the normal, let's say false or whatever. And now if somebody calls a reserve again, you have to start from the beginning in order to find out that, hey, what is the first index which is not yet occupied, right? So these are the things that you would have to do. Now the point to understand is that your operations here will not be constant time operations. Why they will not be constant time operations? Let's say somebody calls unreserved of a seat number, then you can immediately go to that index and you can convert it to false, right? So whatever is the value of seat number at that particular index of the array, we can mark a false, correct? Right? So this function can be implemented in order of 1 time, but this function will definitely take you order of n time. Why it is taking order of n time? Because you will have to iterate from the beginning to figure out what is the first place where reservation is not there. You'll have to do all that, okay? Because you don't know in what order reserve and unreserved methods are going to get called. They can get called in any order, and because of that there can be sparse collections of trues and false, whatever you have. Does it make sense? How many of you absolutely understand this small little idea? Yeah, simple enough. If let's say somebody was to implement it, what he or she can do is can say that, let's say we have a vector int whose, let's call it seats, okay? Now what I'm going to do is that I'm simply going to when this constructor has been called, that means we are initializing this seat manager class. So I am going to push some items inside it, in fact n plus 1 items. Why I'm saying n plus 1 items? Because as I told you, I'm going to ignore the index 0 and I'm only going to consider index 1 to n. So I'm going to do something like this: for int I equals 0, I smaller than equals to n, I plus plus, and I'm going to say seats dot push back 0. So initially all these values are 0, 0, 0, 0, 0. So basically all the seats are 0. That means all the seats that you have are currently your unreserved seats. None of them have been reserved. Okay. Now whenever somebody reserves a seat, what is it that we are supposed to do? We learned that we have to iterate from the beginning and we have to find the first point where the reservation is not there, right? So what we can do is we can just iterate from 1 all the way till n, right? Also this n is important to us, right? This n which has been passed, So you can simply say I smaller than seats dot size. It will take care of that. Okay, I plus plus. At this point of time, while you are iterating, if you happen to see that seats of I is 0, if it is 0, that means ith index corresponds to the seat which is empty, which is not reserved yet. So in that case, what we can do is, because that's being reserved, so the first thing we will do is we will mark it as reserved. So we will say seats of I should now be converted to 1, and then I will return the value I from here. Works well. Okay, cool. In case of unreserved, what we are supposed to do, so whenever somebody wants to unreserve a particular slot, then in that case we are simply going to do seats of that seat number, and we are going to be marking it back to 0. That's it. This is all that we are doing. So this code is consistent with whatever we have discussed. Now let's run it and see what happens. Okay, here we need to return some default value at the end so that it does not complain. So let's say, although we'll never return it, because I think our inputs are never going to be like that, where we will run into a situation where somebody is reserving and the seats are not there. So we can safely assume that. Works well. So if I submit it, you can clearly see that it is the case of time limit exceeded. So time limit exceeded means that the complexity is not great, and I can see it is not great because what is the complexity of reserve method? The complexity of reserve method in the worst case will be order of n, because the size of this vector is order of n. Correct? So now we need to do better. There comes the idea of heap. So if you do not know about heap, now is not the right time to talk about it, because I need a full-fledged class to talk about it, to illustrate it so well to you. But I can definitely give you a high-level overview of what heap is. First, it is an incredibly important data structure, and there are so many interview questions which are based on heaps. If you really know how to use heaps to solve questions, then you will be able to solve a lot of beautiful questions from greedy algorithms. And greedy algorithms happens to be one of the most hardest algorithms, I would say, to understand and prove their correctness and all. Anyways, so what is a heap? Heap is a data structure which is also known by another name, priority queue. You might have heard of it. Priority queue. Now by default, what this priority queue does is, by default, it maintains an ordering of max. So what I mean by that is, let's say there is a priority queue in which items are 10, 1, 7, 8, 6 and 4. So if you have a queue, and if you ever pop an element from this queue, then you will get the largest element. So let's say you pop from the queue, you will get the largest element, which is 10. Okay. If you pop again, you will get the largest element, which is 8. If you pop again, you will again get the largest element. So this is how priority queue works. So how does normal queue function? If you have a normal queue, then there is a front end, there is a back end. So you push at one end and you pop from another end. There is no ordering. But in case of heap or a priority queue, there is an ordering. So by default, the ordering is max based ordering, that whatever is the maximum element, you are going to get that. As simple as that. Okay, now declaring a priority queue kind of data structure in any language, be it C++, Java, whatever you are using, is super easy. You can simply say that, hey, I need a priority queue of integers, and you can give it any name. Let's call it seats. See, this is where the knowledge of data structure comes in handy, right? Why do we learn data structures? To optimize questions like these, right? Okay, so now that you create this priority queue, in case of priority queue, if you want to insert an element, or you want to delete an element, the complexity is order of log n. And log n is much smaller than order of n. In this case, this method was taking order n time, right? But if we use a priority queue, we can do our operations in order of log n time. In just order of log n time, we'll be able to extract whatever is the maximum or whatever is the minimum, right? So that's the purpose of it. Now, if you're wondering that, hey, how the operations are done in order log n time in case of a heap, then that needs a complete understanding and study of heaps. Okay, and we are not going to do that today. I'm just going to tell you on a high level that it is going to be order of log n. Okay, heap is a tree-based data structure, so it creates a balanced binary tree kind of thing. And because it's a balanced binary tree, so the height is log of n, right? And because of that, the insertions and deletions that happen is of order of log n. Okay, it's not a binary search tree, by the way, so don't confuse. It's very much different than binary search tree. Okay, I didn't understand why you put break in reserve. I didn't understand why you didn't put break in reserve. Because I am returning no. The moment you return, there is no need to put break. Return means exit. It's complete exit, right? Okay, cool. So that was little overview about what priority queue is. Now, as I told you, with case of priority queue, by default it is always going to return you the maximum value. It is not going to return you the minimum value. So another thing, in this case, the seats that we have are numbered from 1 to n. So let's say the value of n is 5. The seats are 1, 2, 3, 4 and 5. Now the question is, can we somehow use our priority queue to return us minimum element? By default, it will return you maximum element, but can we somehow use it so that it returns us minimum element? So for that, we can use a cool trick, and it's a very handy trick. What we can do is that whenever we are pushing an element inside the priority queue, okay, then instead of pushing the element, we can push the negative of it. So instead of 1, we will push -1. Instead of 2, we will push -2. Similarly, -3, -4, -5. Now a lot of you might have understood my idea. At this point of time, if priority queue behaves in a default manner, what will it return? Will it return -5 or will it return -1? What do you think? It will return -1 because the maximum value out of all these values is -1. Now the moment it returns you -1, you know that nothing can be negative, so you can do a multiplication with -1 and you can get to know the actual seat number, which is 1. So it's just a trick, it's just a simple trick where instead of pushing the seat numbers, I'll be pushing their negations. When I push their negations, it is guaranteed that the smallest seat number would appear to be the one having the maximum value. Could you follow me on this small little trick? Did that make some sense? Yeah. But why aren't we using a minimum priority queue? You can. I never said you cannot. You definitely can. The only thing is you will have to write your comparator. So if you know how to write comparators and all, please go ahead and use it. Okay? There's nothing wrong with it. Cool. So I'll just show you some code. I think I have written it beforehand. It's a very simple code. So you can see, like in our brute force code, we had a vector of integers. Here we have a priority queue of integers. Okay. To start with, I have pushed everything from 1 to n in my priority queue. But I have not put those numbers, rather I have put the negation of those numbers. And I believe you understand why I have put negation of those numbers. Okay. Now, whenever reserve method is called, I am doing seat nums.top. See, whenever you call top method, top is a method associated with a priority queue. So whenever you call this method, it will return you the maximum element by default, and we have to multiply -1 with it. I explained why, right? That way you get the seat number, and now you can remove it. So what top does? Top simply returns you the maximum value. It does not delete it. Okay, so let me just write it here for those of you who are new to priority queue. There is a method called as top. It simply returns you the maximum element. It does not delete it. And then there is another method called as pop, which deletes it, which deletes the maximum element. Now that you are clear with these two things, you will be able to relate to it. So first I read the element, which is maximum, and then I kicked that element out as it is no longer needed. And then I returned the seat number. So that is a simple implementation. Unreserve, what we will do in unreserve? So let's say somebody wants to unreserve a seat. In that case, we would simply want to push it back to a priority queue. So let's say somebody had reserved seat number 1, and now if he or she wants to unreserve it, we need to put it back. But when we put it back, we need to multiply it with -1 and then put it back. Putting back means pushing it inside the queue. So that's it. These are bare minimal lines for the code that we have, for the logic that we discussed. Does it make sense? How many of you understand this idea? Which is a better way, negation or comparator? I mean, it depends on so many factors. If you are sitting in an online coding assignment, you do not have a lot of time and you have forgotten how to write your comparator, let me ask you, what will you do? What will you do in that case? If you are sitting in an online coding interview and you have forgotten how to write comparator, in that case you would probably go ahead with this cool little trick only, right? But now let's say you are in a face-to-face interview with your interviewer, and your interviewer wants to test your knowledge of writing comparators. There you have to be able to write comparators. So you can't run away from any of these. Knowing all of them is always the safest option. Yeah. Okay, cool. Yeah, now let's talk about few things. What is the time complexity of this method now? The time complexity of this method depends upon the time complexity of pop, which we all know is log of n. Similarly, the time complexity of this method depends upon the time complexity of this, which is log of n. So in the current solution, this also has a time complexity of log n. This also has a time complexity of log n, right? In the previous solution, this had a time complexity of order n. This was order 1, so that was good, but this was order n, and n is so high. That was the reason we were getting time limit exceeded. But in this case, you won't get that. Okay? Is it clear to everyone? Now, there is one more thing. You know, it's just a scope of improvement for everyone. If I ask you that, hey, how much time will I spend here? What will be the time complexity of this particular constructor call? Or what will be the time complexity of this much of code which I have shaded? Somebody is saying n log n. Okay. See, what did we learn? We learned that whenever you push something, the complexity is log of n, where n is the current size. Okay. I can say when I will be pushing the last element. So let's say when I am pushing the last element, which is n, then before n I would have pushed around roughly n elements. So it would have taken me log n time to perform that push. Similarly, while I would be pushing n minus 1, then just before pushing n minus 1, I would roughly have pushed n minus 1 elements, right? So that would be log of n minus 1. So you know, your operations, the operations that you are doing, those operations are not of constant time. In fact, the complexity of those operations depend upon what is the size of your heap currently, right? So the sequence that you will get will be something like this. It will look like you have done log n operations for the last iteration, log n minus 1 operations for the last second last operation, and it will go on like that. Log n plus log n minus 1 plus log n minus 2 plus log n minus 3, and this will become log of n factorial almost. Right? All of you know that log a plus log b is log of a into b, right? So, and because of that, it will be back to n log n. So the complexity of this piece of code is going to be n log n. But can we reduce it somehow? So what we are doing right now is, beforehand we are initializing a priority queue with n items. But can we somehow do away with this? So again, it's an intelligent idea. It's just a small intelligent idea that we can use. Think of it in this manner, guys. Let's say the seats available were 1, 2, 3, 4, 5 and 6. Okay, these are the seats that are available. Now let's say you have used this seat, so it goes off, it has been reserved, it goes off. Right, now let's say you have used this also, so this also goes off, 2 goes off. You have used 3 also, let's say, so 3 also goes off. Okay. Now at this point of time, like okay, so far, like when you had taken out 1, you very clearly knew that the next seat which is unreserved is seat number 2, right? Similarly, when you had taken out 2, you knew that the next seat which is unreserved is 3. Similarly, when you take out 3, you know that the next seat which is unreserved is 4. Now where does the problem happen? Problem happens when, let's say, you unreserve this 2. If you unreserve this 2, it goes back. At this point of time, if somebody calls a reserve, of course you would want to extract this 2. But when you extract this 2, now would you say that, hey, now the next number should be 3? Would you want to say that? The answer is no. Right? Why? Because this 3 was already extracted. So the problem over here is that when you have extracted a seat which was reserved and then unreserved, in that case you cannot directly say that, yeah, what is your next seat number going to be? But if it is a normal case, if it is a very normal case where you just have 1, 2, 3, 4, 5, 6, and let's say you are just reserving the seats, you are never unreserving any seat, then it is a simple problem, because I know that then I can just maintain a simple variable. Let's say there is a variable x, it is initially 1, you call reserve, then I do x plus plus. You call reserve, again I do x plus plus, again I do x plus plus. So as long as unreserve is not being called, there is no problem. But the moment unreserved for something has been called, there a problem arises, and we need to handle that problem. Are you able to understand my point? How many of you are able to understand my point? Okay, so the basic idea is, what we can do is, we can do something as simple as this. We will have a priority queue in which, to start with, we'll only push one element, that is 1. Okay, now let's say somebody calls reserve. If somebody calls reserve, I'll fetch what is there, I'll get that out. Okay, and then after getting it out, I'll push the next item, which is plus 1 of it. So now I'll push 2. Somebody calls a reserve again. In that case, I'll take this 2 out, and then I'll have 3 over here. This is how it's going to go. At this point of time, let's say somebody unreserves 1. So when somebody unreserves 1, it means I need to push this 1 back into my queue. Now the thing is, at this point of time, if somebody calls a reserve, what will you return? You will return this 1. Okay, so you'll get this 1 out and you will return it here. But will you want to push 2? No, you will not want to push 2, right? So there is an observation that we can make. The observation is, if your priority queue has become empty, let's say at this point of time somebody calls reserve, then it will become empty. So if your priority queue has become empty, that means at that time you can definitely push the next item, right? But if your priority queue did not become empty, that means whatever you extracted was a seat number that you had first reserved and then unreserved. So in that case, you do not need to push. So a simple rule we are going to follow. That simple rule is, whenever we extract an item from this heap, from this priority queue, then we are going to check whether the queue has become empty or not. If the queue has not become empty, it means whatever we have extracted is something that we had unreserved, that we had reserved and unreserved, right? So in that case, we don't need to push the next item. In that case, whatever is the next smallest in the queue, that will automatically be taken off. But if it ever happens that the element we extracted, it made the queue empty, in that case, we will push the next item. That's the simple idea. Does it make some sense? Do you follow it? Right? Because you can understand how the things are happening here. See, whenever you unreserve something, you can only unreserve those seat numbers which you have extracted. And the seat numbers that you have extracted are bound to be smaller than this 4, are bound to be smaller than whatever is your current smallest. So if you unreserve any of them, let's say you are unreserving this 2. If you unreserve this 2, it is guaranteed that this is going to come before that 4. So now if somebody calls reserve, it is guaranteed that this is going to come out. And when this comes out, it is guaranteed that our queue is not going to be empty. If it is not going to be empty, that means, yeah, we still have the candidate for our next smallest, and we don't need to push the item after 2, which is 3. So this is one small improvisation that can be included here. So as you can see, now what I have done is, now I no longer have a loop which is pushing everything from 1 to n. I simply pushed 1, -1 to be like, you know why this is -1. And now what we are going to do is, we are going to extract the seat number and we are going to pop it, and then we have this empty check, that if our priority queue has become empty, then only we are going to push the next thing, otherwise not. So that's it. That's the only change. This solution can probably be claimed as a very good solution, because this does not just involve your knowledge of heaps, but also involves some element of problem solving in general, that you could optimize few things in the runtime by making some simple observations. And to be honest, it was not very tricky, it was not very hard. I mean, if you spend some time thinking around it, then mostly you are able to come up with that. So these were some solutions to this problem. Next, what you should do is, when you go back, code this problem. If you have never studied about heaps or priority queues, try to learn about it from wherever you would like to, because it is very, very important. And whenever you are learning about heap or priority queue, it's always a great idea to implement your own heap ones. Okay, so we will just keep this much for today. I think we met after so many days because I was keeping a little busy, but we'll continue from today onwards. Yeah, okay, then that will be it for today. Let's see you all again tomorrow. Bye and good night.